Um, so today we're going to finish doing the mathematical preliminaries for this class. Um, so we talked about classifying differential equations, and now we're going to talk about the one approach that you're going to need for solving differential equations in this class. It's called separation of variables. And it's my experience that, some of you have taken differential equations already. Some are taking it. Some will take it soon. You're going to learn a million techniques for differential equations, but this is insider information. So this isn't true for electrical classes, but for all your future mechanics classes, if you're ever expected by a professor to solve a differential equation without having discussed specific techniques in the class, okay, you follow what I'm saying? This is the way to do it. This is the only approach to differential equations that you'll ever be expected to conjure up on your own in mechanics classes. Okay? If they give you a differential equation and expect you to solve it, this is how you do it. Okay. So if you remember that, you can look really smart to the people who don't know that. Okay. And the idea of separation of variables is that you're given a differential equation that can be expressed as some derivative, I'll say dy dt, is equal to a function only of y times a different function only of t. So that's separation and separation of variables. You can divide this up into some stuff that only depends on y and some stuff that only depends on t. You can re-express this as dy over f of y is equal to g of t dt. So all I did here was divide both sides by f of y, multiply both sides by dt. That's not really what you're doing. Like really, technically, you should go through some chain rule stuff, but it's perfectly fine to think about it that way. Then just integrate both sides. And use the boundary conditions to solve for the constants of integration. So this technique doesn't, by a long shot, it doesn't work for every ordinary differential equation, but it is pretty flexible in a way. It works for higher order differential equations. You just have to do it in multiple steps. And it also works for linear or nonlinear problems, as long as they're the right kind of problems. So, when you do differential equations, you learn techniques for linear first order, linear second order, all this stuff. Separation of variables crosses all these boundaries. It doesn't work for everything, but it works for some of all these different categories. So here's an example. So let's say we want to solve y dot is equal to y squared t squared, where when time is equal to 0, y is equal to 10. That's y squared t squared. Dy dt. Yep. So the dot always means d dt. Double dot means second derivative with respect to time. Yep. Uh, have you ever seen that? 5 dots? No. I have never seen anywhere. You just keep writing dots. And in dynamics, you never take more derivatives than 2. Because the relationships are between position and acceleration. No, we're not going to do that. Yeah, then you have a lot. Yeah. Um, so the function of y is y squared. The function of t is t squared. So I'll rewrite this as dy dt is equal to y squared t squared. And so divide both sides by y squared, and you get y to the minus 2 dy is equal to t squared dt, and integrate both sides. And so you get negative y to the negative 1 is equal to t cubed over 3. Each of these has a constant of integration. Since they're both arbitrary, I'll just lump it all into a single constant like that. And now we're going to use the boundary condition. To find that constant of integration. When t is equal to 0, y is equal to 10. So what that says is negative 10 to the minus 1 is equal to 0 cubed over 3 plus c. And so negative 1/10 is equal to c. And so we can rewrite this relationship as negative y to the minus 1 is equal to t cubed over 3 minus, I'll do it as 0.1, minus 1/10. Okay, so now we've defined the relationship we want, but really ideally we'd like to express, we'd like to come up with a function y of t, so we just have to do a little algebra here. So I'll write this as 1 over y is equal to negative t cubed over 3 plus 0.1. And get a common denominator here. So we have negative t cubed plus 0.3 over 3. And now we can take the reciprocal of both sides, and we get that y as a function of time is equal to 3 over the quantity negative t cubed plus 0.3. Any questions about that? I forgot to go through all the classification stuff. I'll do that on the next example. But if we would have done that, we would have seen it was an ODE. The independent variable was time. Dependent variable was y. That's what we're trying to find y as a function of time. And it was first order, so we needed one boundary condition, which we had. And we were ready to go. Yes? Yeah. Mm-hmm.
So when we're looking at the problems, what will we see in our problems?
Mm-hmm.
Are we going to see the
So what we'll see in problems is, like, for example, so it will occur like an object's, well, there's a few ways it could. So let's say Newton's second law says that sorry. So let's say that the net force on an object is p squared cosine of p. So then Newton's second law says, well, I didn't give anything. So, let's say that we want to find, and let's say the mass of the object is 0.5 kilograms. And we want to know what's the position as a function of time if the position and velocity are both 0 at time equals 0. Then Newton's second law, bless you, says the net force, t squared cosine t, is equal to the mass times the acceleration. The mass is 0.5. The acceleration is the second derivative of the position. And we're given the boundary conditions that p of 0 is 0 and v of 0 is 0, which it also says p dot of 0 is 0. Okay, so now what we have is we have an ODE. Our independent variable is time. Our dependent variable is p, so we're trying to find that position function. It's second order, which means we need two boundary conditions, and we have them, so we're ready to solve this problem for position as a function of time. Okay, so the way differential equations come up most often in this class is that velocity's time derivative of position and acceleration's time derivative of velocity. Okay, so this is a second order. Let's see how this works with a second order differential equation. So let's say that the differential equation is x double dot is equal to 2t squared. Where when time is equal to 0, x is equal to 2. And when time is equal to 2, x dot is equal to 4. Okay, so first let's classify this. Then it'll be classified information. Highly classified. Don't patronize me. So is this ordinary or partial? Yep, it's ODE. So what's the independent variable? T. What is or are the dependent variables? Yep, trying to find the function x of t. What's the order? Yep, second order. ODE. And so how many boundary conditions do we need? Yeah, need 2 boundary conditions, and we have 2. That's what these are. Like I mentioned last time, that doesn't necessarily mean that those boundary conditions are going to work, but if you don't have 2 boundary conditions, you know it's not going to work. Okay, so we're ready to try this. Thanks. So what are we going to do with this second order derivative? I'm going to rewrite this as ddt of x dot. So we're going to start by finding this variable x dot is equal to 2t squared. And so separation of variables says dx dot, this is sort of a weird notation, but is equal to 2t squared dt. And we're going to integrate both sides. The variable we're dealing with here is x dot. And so when we integrate the left side, we get x dot. You can think of this x dot, you could replace that with y or z or something. And when you integrate dz, you get z out. And so you get x dot is equal to 2/3 t cubed plus c. Let's call this C1. We're going to get another one when we integrate again. We actually, in this case, we have a boundary condition that depends on x dot, so we could solve for that constant integration right now, but let's just push it all off till the end and then deal with it. Okay, so here's our first, we've made the first step. Now I'm going to rewrite x dot as dx dt. That's equal to 2/3 t cubed plus c1. And so dx is equal to the integral of all this stuff with respect to time. And you get that x is equal to 2/12 or 1/6 t to the 4th plus c1t plus c2. And now we'll use the boundary conditions to find c1 and c2. The first one says when t is equal to 0, x is equal to 2. So 2 is equal to 0 plus c2. I just plugged 0 in for time in this function and said that the value, when time is equal to 0, the value of x is equal to 2. And so that tells us that C2 is equal to 2. And now I can update that function. We have that x of t is equal to 1/6 t to the 4th plus c1t plus 2. The only thing we still need is that c1. Well, we have an expression for x dot there. We could just take the derivative of our updated function again. Boundary condition says when time is equal to 2, x dot is equal to 4. So 4 is equal to 2/3 of 2 to the 3rd plus c1. Is that right? Yes. Any questions about where I got this expression? And so 2/3 of 8, 16/3. So 4 is equal to 16/3 plus c1. So that is minus 4/3. And now we can give the final update. Now that we know C1, we know that the function x of t is 1/6 t to the 4th minus 4/3 t plus 2. Any questions about that? We also are going to sometimes have to deal with systems of differential equations. And for us, well, here's an example of a system. So let's say x dot is equal to 5xt. Y dot is equal to 2y squared t squared. Where x of 0 is 1 and y of 0 is 5. Systems of differential equations can be complicated if the system is coupled. If it's not coupled, then you can do it as two separate differential equations. So the key is in this class, these are always going to be uncoupled, meaning that each dependent variable variable stays in its own equation. You can see that this is an example of an uncoupled system because there's an equation that only deals with x. You know, we have x dot and x, and a separate equation that only deals with the other dependent variable, y. This said x dot is equal to 5xyt, then that would make that a coupled differential equation, and there are ways to deal with those, but we're not going into that. And those aren't going to come up real naturally in dynamics anyways, so. Any questions about the coupled, uncoupled distinction? All right, well, let's solve this example. So I'll do x equation first. Dx dt is equal to 5xt. So dx over x is equal to 5t dt, and we'll integrate both sides. We get that natural log of the absolute value of x is equal to 5 halves t squared plus, I'll call that C1. There's no such thing as natural. Oh no, x. Okay, x is equal to 1. Okay, so we're dealing with positive x's. And so we're going to be dealing with natural log of x is equal to 5 halves t squared plus C1. The boundary condition says natural log of 1 is equal to, so what the boundary condition says is when time is equal to 0, x is equal to 1. So we have natural log of 1 is equal to 0 plus C1. Natural log of 1 is 0. So C1 is equal to 0. And so our equation says natural log of x is equal to 5 halves t squared. That's what I'm going to do now. You can do it before you use the boundary condition or after. You know what I mean? Before the boundary condition, I could have expressed x as a function of time before that and then used the boundary condition, but I just embedded it in that, mixed up form. But yeah, so now I'm going to raise both sides to the, e to each side. So e to the natural log of x is equal to e to the power of 5 halves t squared. And that says that x as a function of time is equal to e to the 5 halves t squared. We could do the x equation as if there was no y equation because it's uncoupled, And now we'll go to the y equation. The y equation says dy dt is equal to 2y squared t squared. So we have y to the minus 2 dy is equal to 2t squared dt. Integrate both sides, and you get negative y to the negative 1 is equal to 2/3 t cubed plus a constant I'll call c2. The boundary condition says that when time is equal to 0, y is equal to 5. So we have negative 5 to the minus 1 equal to 2/3 0 cubed plus c2. So c2 is equal to negative 1/5 or negative 0.2. So negative y to the negative 1 is equal to 2/3 t cubed minus 0.2. This looks a lot like an example we did just a minute ago. So 1 over y is equal to negative 2/3 t cubed minus 0.2. Yes, thank you. Get a common denominator, and you get negative 2t cubed plus 0.6 over 3. And then reciprocal of both sides says y as a function of time is equal to 3 over the quantity negative 2t cubed plus 0.6. And the way this is going to come up in our problems usually is sort of what this suggests, that we're going to have separate functions representing the x component and the y component of the position, and we'll just solve those separately because they'll always be uncoupled from each other. Any questions about that? Okay, so we're almost done. We're not, I think we'll finish this today. So here's where we are with the mathematical preliminaries. The first one is solving ODEs using separation of variables. The second one is derivatives of vectors. And I didn't mention this before, but it is an important distinction that it's going to be important later on. We're talking here about how to take derivatives of vectors in non-rotating coordinate systems. Later in the class, we're going to be doing calculations where the coordinate system is rotating, and we'll see that this doesn't hold anymore. Third is product rule with vectors. And fourth is the chain rule with vectors. We're done with this one. So it looks like we're a quarter done, but we'll finish in the next 15 minutes, I think. Okay, so the second one is derivatives of vectors in non-rotating coordinate systems. And that's going to be important because the velocity vector is the time derivative of the position vector. The acceleration vector is the time derivative of the velocity vector. And the angular acceleration vector is the time derivative of the angular velocity vector. Omega, Greek omega. So to do this, it probably works. If you had to guess how it works, that's how it works. Or if you have a vector u that's a function of time, and I'll write that as, a x component, a y component, a z component. Then the time derivative of u is just the time derivatives of each of those components. So ux dot, uy dot, and uz dot. And when we start doing rotating coordinate systems, we'll see that's not true anymore. But in non-rotating, that's true. I don't think you need an example of that. You just take the time derivatives of each of the components. So let's go on to product rule. Well, it depends what it's representing. Yes, actually, it doesn't matter what it's representing. Yes, you always just go element by element and take the derivative. Product rule with vectors. There are a few types of products that come up with vectors. Remember, you can multiply a vector by a scalar. You can take a dot product with two vectors. You can take a cross product with two vectors. So if you multiply a vector by a vector by a scalar, ddt of, let's say we have a scalar x and a vector v. That's equal to x dot times the vector v plus x times the vector v dot. Again, I should say all these product rules are if you had to commit to something on paper, had to guess how these product rules would work, it does it just like you would think. Yep. No, a scalar doesn't have to be a constant. Like this could be a function of something. Okay, it just means it's a number. It's not a vector. Right. Yep. Exactly. Then the next thing you can do is dot product. And so if you're taking the derivative of u dotted with v, that's u dot dotted with v plus u dotted with v dot. And then the cross product. So notice, I mean, these all follow the exact same rules. Notice that, and then you save storage space in your brain. You just have to remember it once, you know what I mean? The cross product, so let's say we're taking the time derivative of u crossed with v. That's u dot cross v plus u cross v dot. And I want to show you one pitfall to be careful with, careful about. This, we could rewrite that as x dot v plus v dot x. Right, if you like that format. I don't know how you're used to formatting product rule with scalars, but say you like to put it in this order where you always have the derivative first or always have it last. No problem here. Right? Same here. No problem. You could write this as u dot dotted with v plus v dot dotted with u. That breaks down here though, because the order matters with the cross product. So this is not equal to u dot cross v plus v dot cross u. Okay, so you got to get that order right. I would just get used to doing it in this order with everything scalars, multiplying by scalars, dot product. Any questions about product rule? And then the last one is the chain rule. So the general chain rule says I don't think I'm going to give you that general one. In our case, since we're only dealing with a single independent variable, the time derivative of a function of another function is df dg times dg dt. And if that f is a vector, So now that function f has components, but all of those components depend on some function g of t. You just get derivative of that vector f dg times dg dt. And the most common way that this is going to come up in dynamics. So the chain rule comes up in dynamics like this. We know that the acceleration is equal to the time derivative of the velocity. Right? But what if the velocity is given as like v of x, meaning, and this is a vector. So let's say that we know the velocity as a function of its position, some position variable. So the velocity is a function of a position variable. Well, like if we're given that the velocity, as the thing moves along the x-axis, let's say the velocity is x squared for the x component, negative 2x for the y component. We can't take time derivatives directly because we don't have it expressed in terms of time, right? So it looks like a problem, but look at this is a really slick little trick that's going to come up over and over again. So we can't take d dt directly because we don't know that function. But the acceleration is equal to the derivative of the velocity with respect to x times dx dt. And this, if you take the time derivative of a position variable with respect, take the time derivative of a position variable, you get a velocity variable out, This is a velocity component. Okay, so using the chain rule, you take the time derivative of the velocity vector without knowing what the velocity is as a function of time. It's going to be a really useful thing. This idea also works with rotations. With angular quantities. The angular acceleration is equal to the time derivative of the angular velocity with respect to some angular position times d theta dt. And this is an angular velocity component. Anybody have any questions about any of that? All right, well, that's it for today. So we're done with math, and we don't have class on Monday, Martin Luther King Day, but on Wednesday we'll get into particle kinematics. Okay, and look on D2L in the next few minutes, I'll post the assignment for until Wednesday. Okay? Yes. But we will we'll do a ton of problems like this, and I'll talk about it in more detail when we get to it. For now, I just wanted you to sort of see that this is a thing, but I'll give you plenty of examples when you need them. Okay? Yeah, right. It should be.